Today we will discuss the most general many-body systems of Calogero-Moser type, elliptic with elliptic interaction. When the potential of interaction between particles is given by the Weierstrass P function. Last time I explained you the general method of proving identities with elliptic functions, and now I would like to demonstrate it on an important example. Let us consider the identity for Weierstrass sigma function. Let us prove it. Divide everything by this term. Then we get and the identity states that this is -1. How to prove it? Consider the left-hand side denoted by some f. Consider it as a function of u. A, B, C, D are some A, B, C are some parameters, and U is variable, living on the complex plane. What we can say about this function? First of all, we note that it is double periodic elliptic function of U. Indeed, we have here sigma of U plus C, sigma of U minus C in the numerator, and in the denominator we have this. So if we recall that sigma, when we shift by periods, this function acquires a multiplier, which is exponent of some linear function of U. That is why this exponent cancels in this expression, because here we have plus C minus C, plus B minus B, and if you substitute this multiplier here, you will see that it cancels. So this A and B depend on alpha. Alpha is 1 or 2. Okay, so and the same is in this term, plus a minus a, plus b minus b. So this factor cancels. So this function is double periodic. Now let us see where it can have poles. Possible candidates for poles is, for example, this term, this factor which is 0 when u equals b. So we have 0 in the denominator, so this is a pole, first order pole. And also we have this. And so we should check 2 points, u equals plus minus b. These are points where possible poles can appear. So let us check, find the residue at for example, in the pole at B. We have we substitute B instead of U here and here. And here we have sigma of 2B. This is the coefficient in front of this pole. Now, what we have here? Now you see that that the sum is 0 because this coincide this are the same. This is the same, and these factors are equal with different signs. So we have 0. So the residue of this pole is 0. And in the similar way, you can check the second possible pole at minus b, and you will obtain that the residue is 0. In fact, this second pole, it is clear that the residue is 0 even without checking it explicitly, because we checked that there is no pole at B, so this function could have a single pole at minus B, first order, but this is impossible for elliptic functions, because the sum of residues must be 0. So we conclude that this is a regular elliptic function. Therefore, it is a constant. To find the constant, we can substitute some particular value of u. For example, such that the second term becomes 0 when u equals a. Then this vanishes and the whole term vanishes. And what we obtain here? I substitute a instead of u. There are many cancellations. And we are left with this and this, so this is -1. So the identity is proved. I remind you that last time we introduced Weierstrass functions sigma, zeta, and p. P is elliptic function, double periodic, which has a second order pole at the origin and in all points of the lattice. We will also need another function which is called Lamé-Hermite function. It is given by the following formula. This function is double periodic in lambda. But in X, it is not double periodic, and the monodromy property is like this. Eta is a constant which here is the monodromy of zeta function. So this factor does not depend on X, just some multiplier, which is sometimes called Bloch multiplier. At the origin, this function has a first order pole in X. So it is 1 over X minus 1/2 pi of lambda X. Note that the constant term is missing. It cancels because of this factor. This function satisfies some identities, and we will need them for the calculations. This one easily follows from the definition and from the definition of zeta function. You just take logarithmic derivative of this function and immediately obtain this identity. The second identity is more, the proof of second identity is a little bit more complicated. But can be done using the same method as I explained. and another one. In fact, it can be obtained by differentiation of this one with respect to x and y. Okay. Now let us introduce the elliptic Calogero-Moser system. The Hamiltonian is so this is instead of 1 over x squared, we have this Weierstrass function here. And the Newtonian equations of motion are of this form. These equations of motion have Lax representation. But now L and M matrices satisfying the Lax equation depend on additional parameter lambda, which is called spectral parameter. And they can be written in terms of this Lamé-Hermite function and its derivative with respect to x, first variable. And the matrix elements are as follows. Problem. Even two problems. So we have the Lax equation. And the first problem is to prove that the equations of motion are equivalent to this Lux equation, which is valid for any lambda. And the second problem is to find trigonometric and rational degenerations of this Lux pair. You will obtain trigonometric and rational Lux pair, but depending on the additional parameter lambda. This is what I told you before, that the Lux representation in rational and trigonometric case is not unique. You can introduce additional parameter, which is this lambda. But in rational and trigonometric case, there is a special point in lambda when lambda equals infinity, some distinguished point. In the elliptic case, when lambda lives on the torus, on the fundamental domain, which is have rectangular form with identified opposite sides. So this is a torus. And there is no distinguished point on the torus, so lambda, all points are on equal footing. And of course we can fix lambda in some way, for example, to put it equal to sum of half periods. And in this form, this Lux pair with some fixed lambda was found for the first time. But then Ruijsenaars showed how to introduce this parameter, and the Lux pair was written. There was discovered the Lux pair which depends on the spectral parameter. And this spectral parameter is important because
any explicit dependence on periods.
Yes, everything depends on these periods.
But there are no differences in how we choose them. So all is valid for different periods.
Yes, and trigonometric limit means that one of the periods tends to infinity. And rational limit means that both of them tend to infinity.
But you just said that we can take a limit in lambda to reach some.
Yes, but on the torus, there is no natural way to choose any special point. When one of periods or both are equal to infinity, then such a point is infinity. And the expression for the Lux matrices simplifies at this point. When you find how these formulas degenerate in trigonometric or rational case, you will see that after that, tending lambda to infinity makes the formulas simpler. Another problem is to find, to prove that trace of L squared gives our Hamiltonian plus some constant which depends on lambda, and also find trace of L cube as a function of lambda in explicit form. And general integrals of motion are traces of powers of lambda. But now this expression can be represented as a linear combination of the Hamiltonian HK and other Hamiltonians, lower Hamiltonians up to H1, with coefficients depending on lambda. In rational and trigonometric degenerations, when we tend lambda to infinity, these coefficients vanish, and we are left with the highest Hamiltonian. But in elliptic case, it is more complicated. We have the whole linear combination, and there is some not so simple problem to find how to define higher Hamiltonians. And the answer to this question can be done when we consider dynamics of poles of elliptic solutions to the Kadamov-Petriashvili equation. And it's possible to, there is some natural way to define high Hamiltonians considering this dynamics of poles. And another important object related to this model is spectral curve. Consider the characteristic polynomial of the Lux matrix. This is identity matrix. So this is n by n matrix. It is a polynomial in Z of degree n. And this is because the Lux equation states that the time evolution is an isospectral transformation. This is spectral invariant, and it is conserved in dynamics in all higher flows. And if we equal this to 0, consider such equation R of Z lambda equals 0. This gives us a curve, which is called spectral curve. And this curve is a very important object in the theory. Of course, this is a curve in complex sense, so both Z and lambda are complex variables, so the real dimension of this curve is 2. So from the real point of view, it is a surface, some Riemann surface. Let us call it gamma, this curve. And by construction, we have a covering of original elliptic curve with periods 2 omega 1 to omega 2, and this spectral curve. This covering has n sheets. Here we have a torus, and above each point on the torus, we have n sheets. This equation has n solutions, and for Z, and they correspond to different sheets of the covering. Now let us investigate in some more detail the properties of the elliptic curve. The Lux matrix has essential singularity at lambda equals 0, because you remember this function contains a zeta function in the exponent. So this is this factor because when lambda tends to 0, this zeta function tends to 1 over lambda, and this the point lambda equal to 0 is essential singularity for this function. To get rid of it, one can consider a gauge transformation. Introduce another Lux matrix L tilde, and G is a diagonal matrix with and this factor just just xi. And this factor cancels the essential singularity. In the definition of the spectral curve, we can put here tilde. And then we see that this determinant can be represented as a polynomial in Z with some coefficients which are elliptic functions of lambda. All of them are integrals of motion. Example for n equals 2. Problem is to find for n equals 3. In a neighborhood of lambda equals to 0, the matrix L tilde has the following form. The first leading term in the expansion for small lambda is like this. So this singular term, and after that, there is some regular expression. And this matrix E is the matrix with all matrix elements equal to 1. This is a rank 1 matrix which has eigenvalue 0 with multiplicity n minus 1 and another eigenvalue n with multiplicity 1. So we can represent the equation of the spectral curve in the following form. Where these functions fi are regular in a neighborhood of 0.
I think that this fact about e minus I and minus I is not true because this matrix don't have such eigenvalues.
This factor corresponds to this eigenvalue, and these factors correspond to n minus 1 eigenvalues equal to 0.
Since the trace is invariant, we should have that trace is equal to 0. E minus I trace with this matrix
Yes.
is 0, but when we have zeros and n on the diagonal,
But some of them, if you take a sum of this and all this, you get 0. N minus 1 here minus 1 times to n minus 1. So this is 0.
I've obtained that there are n minus 1 eigenvalues with the value minus 1 and 1 eigenvalue with value n minus 1. So multiplicity of minus 1 is n.
No, here we have eigenvalues of this matrix. So this eigenvalues minus 1. Because of this, we have minus 1 here and minus 1 here. So different when lambda tends to 0, we have n solutions. If we put this equal to 0, so we consider equation of the spectral curve, we see that here is the point 0. This is lambda. Lambda lives on the torus. And we have a covering. And here we have n sheets. And above 0, there are points which are points at infinity. Let us denote them by Pj. J runs from 1 to n. And from this formula, you see that one of the sheets is distinguished. This one. These are the same, and this one is distinguished. and let us call it upper sheet. So around each point here we have the leading term is lambda minus 1, and on the upper sheet we have another asymptotics with different coefficient. And it remains to find genus of the spectral curve. For this, we need the Riemann-Gurwitz formula. Suppose we have two Riemann surfaces, x and y, and x covers y, and suppose this is n-sheet covering. Then and g of x is genus of x, and g of y is genus of y. Then the following relation holds, which is called Riemann-Gurwitz formula. And EI are ramification indices, because this covering is in general ramified. There are so this is y, and this is some sheets of x, but sometimes at some points the two sheets can there are ramification points, like when you take z to z squared, then you some 0 two sheets of this Riemann surface are glued together, and we obtain ramification points. For algebraic curves, the number of ramification points is finite, equal to some m. And this index is equal to 1 when the point is not a ramification point, and for simple ramifications, when two sheets meet together, this corresponds to value of EI equal 2. And this is a case of general position. There can be more complicated ramifications when, for example, 3 different sheets meet together and so on. In this case, EI equals 3. But these are rather special cases. In general position, all ramifications are simple, like this. So this is the formula, which is proved in advanced courses of theory of Riemann surfaces. And the idea of the proof is triangulation of the base curve and on the covering curve. Triangulation means represented as a combination of triangles with some vertices and edges. And there is a formula which connects the number of vertices, edges, and plaquettes, with genus of the surface where we draw this triangulation. So let us apply this formula to our case. In our case, this is elliptic curve, and this is x is our spectral curve gamma. Then genus of elliptic curve is 0, so this term cancels, and we get the relation. And suppose we are in general position, so all ramification indices are equal to 2, then the right hand side equals just m, the number of ramification points. To find this number, we should characterize what is ramification point algebraically. So we have equation of our spectral curve. At the ramification point, the derivative of this function with respect to z is 0. So these two equations should be satisfied simultaneously.
Excuse me, if this derivative is taken on the coverage space, yes?
Yes, with constant lambda.
How do we define this derivative between two sheets?
But if you take derivative, this is a polynomial of z. So you would just take its derivative. No problem. Let us differentiate this. You can see that this function, this derivative, has simple poles on that all solutions of that equation lie above the point lambda equals 0. And in all sheets except the upper one, the multiplicity of solution is 1. Is 1, 1, 1. But on the upper sheet, you have a pole of degree n minus 1. So overall, you have 2 times n minus 1 poles. But this function is meromorphic, and any meromorphic function has the same number of poles and zeros. So in our case, it's simpler to find poles of that function. But we know that the number of its zeros is the same. But zeros are distributed somehow on other part of the surface, not not above the point lambda equals 0. So our m is equal to n minus 2. Therefore, we can find genus which is equal to n. We should note that this spectral curve is in fact a singular curve. It's not absolutely smooth, because in general position, when you have an n sheet covering of an elliptic curve, the genus of the covering, when this is absolutely smooth, is equal to so it grows like n squared when n tends to infinity. So it's bigger than n. This means that this curve has singular points. The spectral curve can be defined also in trigonometric and rational cases by the same equation. And the problem for you is to write equation of the spectral curve explicitly, for example, in trigonometric case. To do that, you need first to find the Lax matrix as a function of lambda. But in trigonometric and rational cases, this curve degenerates and becomes a rational curve with some singularities like double points, this double point, or cusps. This is a cusp point. Okay. So this is probably all what I wanted to say about elliptic Calogero-Moser model. We will continue the discussion later when we pass to dynamics of poles of elliptic solutions to Adamsov-Petriashvili equation, and we'll obtain this Lax pair in this framework. And now we will pass to Ruijsenaars-Schneider systems. In fact, the Calogero-Moser systems admit deformation, one parameter deformation, which is called eta. Algebraically, it is can be arbitrary complex number. When eta goes to 0 in this limit, we get Calogero-Moser systems in the limit. And rational, trigonometric, and elliptic cases, all of them can be deformed to Ruijsenaars-Schneider models, rational, trigonometric, or elliptic. And we will start. These Ruijsenaars-Schneider systems were introduced in 1986 or 7. I forgot. As relativistic deformations of Calogero-Moser system. And this parameter eta is then interpreted as inverse velocity of light. But these models are also integrable, so this deformation preserves integrability. These models have lax representations and so on. And we will start with rational, the simplest case of rational model. And the Hamiltonian can be written in the following way. P and X are canonically conjugated variables. So Poisson brackets between them is delta EG. You see that this Hamiltonian cannot be divided into kinetic and potential parts, like in Calogero-Moser case. And when eta tends to 0, we can extract the leading terms. And they are the following. So here's the highest singularity is just a constant, plus the next two leading term. This is the total momentum. And the constant term is just the Hamiltonian of the Calogero-Moser system. So this is indeed a deformation of the Calogero-Moser system. However, there was a constant g here, which is squared, Coupling constant. From this Hamiltonian, it becomes equal to 1. However, you can introduce this g, modifying somehow this formula. It's convenient to introduce the following notation. Then the Hamiltonian equations of motion can be written in this form. the problem is to find Newtonian equations of motion and prove that they can be written in the following form. You can rewrite this as follows. In the limit, when eta goes to 0, these velocities tend to 1 plus some correction, and these quantities become velocities of Calogero-Moser model. Together with H plus, one can introduce H minus by the formula. Similar, but a little bit different. So now we have minus here. And this factor is the same. The problem is to prove that Poisson brackets between H plus and H minus is 0. This is, if you try to do this, you will see that it is not a very simple problem, because you will need some rather complicated identities for rational functions. Now there is a comment why this model is called relativistic. Introduce H equal to H plus plus H minus, and P equal to H plus minus H minus. So this one is 2 e to the minus 2 and a third quantity called B, which is just coordinate of the center of masses. And the problem is to prove the following algebra for Poisson algebra for these functions. This is the same as this. And this algebra is Poincaré Poisson-Poincaré algebra. After quantization, you should write here commutators, and then it becomes Poisson algebra of relativistic systems. Because of this, this system is called relativistic. However, its interpretation in terms of relativistic mechanics is not so natural and not very clear, actually. Here you have square roots in the Hamiltonian. It's not always convenient to work with square roots, and there is a way to get rid of them, just making a gauge transformation. And the transformation, it's canonical transformation. This exponent transforms into and xi becomes the same. The problem is to prove that this transformation is canonical. And in these new variables after this transformation, the Hamiltonians will be written in the following way. Another problem is to prove that starting from this Hamiltonian, you obtain the same Newtonian equations of motion. In fact, putting here and here arbitrary constants and making all necessary calculations, you will find that you each time you get the same Newtonian equations of motion. So the values of these constants are not very important. And in this form, they are chosen in such a way that to make the limit eta to 0 easier. Now, what about Lax representation? The Lax matrix has the following form. And M matrix is of this form. The Lax matrix can be expressed through momenta if to substitute the expression for velocity. And the problem is to check that the Lax equation is equivalent to the equations of motion. Let us know that the analog of this commutation relation, which was for Calogero-Moser model, it was of this form, and now this is Calogero-Moser Lax matrix, and this Lax matrix satisfies the following analog of this relation. Here, x dot is a row vector, column vector with components being coordinates. So this is a column. And E transpose is a row vector whose all components are ones. So this is some matrix of rank 1. We can consider characteristic polynomial of the Lax matrix, which is integral of motion because of the Lax equation. So this is, and it can be calculated in explicit form using the well-known formula for determinant of this matrix. And the answer is like this. In our case, yi is xi minus eta. And using this, we find for this determinant and this ik are integrals of motion which have the following form. The sum goes over all sets of k indices which are all distinct. In terms of momenta, these integrals can be written in the following form. I is some set belonging to the set of numbers from 1 to n. And the number of elements is k in this subset. In particular, A1 is up to some constant multiplier is H plus. And IN has a very simple form. It is some constant times exponent of the total momentum. All these integrals are independent, and it can be shown that they are in involution. This was done by Ruijsenaars, however, not in a direct way, because calculating the Poisson brackets between these quantities is a very complicated problem. He did it using quantization of this system. It appears to be simpler to find that quantum analogues of these integrals of motion, so they are some operators where p is changed to derivative. So this exponent is some shift operator. And of course you should to take some care about order of these factors and so on, but all this is possible, and it turns out that it is simpler to find that quantum analogues of these integrals of motion are all commute. And after that, you can make the limit, classical limit, and it then follows that classical analogues of them are in involution. This was done by Ruijsenaars. It is convenient to introduce also I minus k, which are already dependent, but it's convenient to use them as well. The definition is like this. And in this expression, what is changed is sign here and sign here. Okay, this system admits trigonometric and elliptic deformations. And in this case, these multipliers are changed by sinus or sigma function. Each factor here changed to when you see xi minus xj, probably plus minus theta, you changed it to sinus, and then to sigma function in the elliptic case. We will discuss these models in more detail next time. Trigonometric and elliptic deformations. Again, in this case, the Lux representation for elliptic model has some additional parameters, spectral parameter, and you can define the spectral curve. In fact, as it became clear very recently, this elliptic Ruijsenaars model admits a further deformation, which makes it to be some strange, very strange system. And this deformed system is most likely not Hamiltonian. We will discuss it next time. For today, it's all.